Hi everybody, today we're going to be looking at Avogadro's constant and mole in relation to calculations, okay? So this is more so of a worksheet. Now if you want to get the theory, I have made a video before this one that explores more so the content and explains what each of these things are, including the molar mass as well. So this one is more calculation focused. So hopefully it will help you in the preparation for your test or exams. So question 1 says this amount of sodium sulfate was placed into a test tube. And the first thing that you want to find is the mole of sodium sulfate. Okay, so I'm just going to make space for it here. So to figure this out, you need to, you know the mass of your sodium sulfate, which happens to be 3.567 grams. The next thing that we need to do, remembering our flowchart, we need to work out the molar mass of sodium sulfate, because our molar mass helps us work out the mole of substance using this equation, mole equals to mass over molar mass. Okay, that's how we get the mole. This is a very important formula. Okay, so our molar mass, we need to take into account 2 sodiums. So 2 times by, if we find sodium on this list here, on the periodic table, we have 23. I'm just going to round it, because I think the VCA one has 23 instead of a more accurate. Anyway, plus sulfur, 1 sulfur, sulfur's 32.066, 32.1 will do, plus 4 lots of oxygens, so 4 times by 16. Okay, and then now we can figure out what our molar mass is. So 2 lots of 23 plus 32.1 plus 4 times by 16. 142.1. Of course. 142.1 gram per mole. Really important to find your units and express them in your calculations. So I've run out of space. I'm just going to find the mole now, and that's done by finding the mole of sodium sulfate using this formula up here. It's mass over molar mass. So mass is this. You don't need to include the unit in the actual division. Okay, so I shouldn't even have that there. Okay, so hard to see where. Alright, of course. So that's divided, and that gives us so 33.567 divided by 142.1 is 0.25. Whoops, I have just done something very strange in my calculator. Okay, right, so 0.25. okay, is that right? 251. Alright, so we've got that amount of mole. Now, you can see that this is a fairly accurate measure, which means that our we need to go up to 4 significant figures. That 3.567, that's very accurate. That has 4 significant figures in it. These zeros at the front, they don't count, they're just place values. So we start from the 2, we count 1, 2, 3, 4. We stop at the 0, we have to look behind. The number behind doesn't exceed 5, so it's just 2510. So that should be, my 0 should be there. Okay, just correct to the right significant figures. So I'll write that again. Mole. Okay, so that's our mole amount. Now, the next question asks us to find the amount of these molecules. Now, if we want to find the amount of them, and the language here is very important, this is the same as number. So it's asking us to find the number of sodium sulfate molecules. So we're looking for capital N of this. Now that means that we have to take, if you remember our table, we take the mole and we times it by the Avogadro's constant, okay, to find number. If we have 1 mole of substance, we'll just get Avogadro's constant. Okay, but we don't have 1 mole, we have this amount. So we have to get 0.02510 times it by Avogadro's constant. Okay, and that will give us the amount of particles. Okay, so in order to do that, we'll just use this amount and times it by, I'm going to do 6.022, just because I know that this calculator isn't the best. 0.15116. 0.15116 times 10 to the 23. And if you use your scientific calculator, it should give you scientific notation. I don't know why that one doesn't. I can fix that up later. 2 times 10 to the 22. So that's how many particles there are. So that's how many of these, if you were to individually count them, in this amount of grams, that's the number of them at the bottom there. So we've just calculated it. We've saved a long time counting. Okay, the next question is a little bit different. It's not something that we've seen before, but you'll get the hang of this. So find the mole of oxygen atoms. So instead of finding everything, we know we have mole of, how much of this we have. That's equal to 0.02510 mole. So what we can do is we can just set up a little chart for now, little table. This is how many sodium sulfates we have, and say this is how many oxygen atoms we have. So when we have one of these, let's say you just have one sodium sulfate and you can see it. It may be a model in chemistry of this particular molecule. So say you have it, you'll be attaching 4 oxygen atoms to it, won't you? Because you know that in every single one of these sodium sulfates there are 4 oxygen atoms. If you had 10 of them, you would actually need 40 oxygen atoms. So what you'll find is that to go from sodium sulfate to oxygen, we actually are timesing by 4. What that means is if you wanted to find the mole of oxygen, you need to get the overall mole and times it by 4, because you know that there are 4 times more oxygen atoms than there are sodium sulfates. And so 0.02510 times by 4, well, that's okay, 1.0. So that's how many mole of oxygen atoms we have. Okay. And then question D asks you, find the number of them that you have. Notice that question C is different. It's asking to find the mole of oxygen atoms. Now that we have the mole, they want the number. So capital N of O. Capital N of O means that you take the mole that you have and you times it by Avogadro's constant. So the mole of oxygen, we already calculated that. And we times it by Avogadro's constant. Okay, so that means 6.022 that means that we have yeah, okay, we have 0.6, I forgot it, 60, 48, 46. And if I just simplify that, it means 6.046 times 10 to the 23. So that's how many oxygen atoms we have. And you can see that it's more than the amount of sodium sulfate, and that's because there's 4 times more. Okay, the next question is find the number of atoms. Now that means that you're looking for first of all, you can figure out, you can actually take the number first of sodium sulfates that we have. We already calculated that. It was 1.512 times 10 to the 22. And the next thing that we need to do after that is we need to find the number of atoms. And so again, I do like to set up a table because I find that it's quite useful. So this is my comparison between sodium sulfate, and on this side we have atoms. So in one of these, the number of atoms that we have, well, we have 2 sodium atoms plus 1 sulfate, so that's 3 already, plus 4 oxygens, so that's 7. In one molecule we have 7 atoms. In, say, 10 molecules we would have 70 atoms. So we're going from there to there by timesing by 7. Okay, so if you want to find the number of atoms, you take that number, you can times it by 7. So you could times by 7, you could times the mole of sodium sulfate by 7, and then you would have the mole of atoms, and then you can times the atoms by Avogadro constant, or you can just times the number of molecules straight away. Alright, so let's find this one. Let's hope that this calculator cooperates. 512 times 10 to the, oh no, okay, I went for it. Great. Times by 7. Alright. We get that. Let me just check. No, Apparently that is scientific. Okay. 3, 6, 9, 12, 15, 18, 21, 22, 23. Okay, 1.058. Okay, so that's how many atoms there are present. Alright, so question 2. Question 2 asks, tells you how much mass of aluminium nitrate there is, and it asks you once again to find the mole of it. So we need a periodic table. I'm just going to grab it from here. If it actually... Okay, so that will be handy. Alright, now find the mole of aluminium nitrate. So the first thing, we need to write the mass of aluminium nitrate is equal to 1.39 grams. So we can work out the molar mass of aluminium nitrate. Now this is going to be, so we've got aluminium, we need to find aluminium on our periodic table. There it is. We need nitrogen, we need oxygen. Okay, so aluminium is 26.6 and there's only one of them. Now this is a bit harder, so the nitrogen here is 3 because the outside bracket matters, and then it's 3 times 3 for oxygen. Okay, so plus nitrogen, which is 14 times by 3, plus 9 times by 16. So that should give us the molar mass that we're looking for. So 26.6 plus 14 times by 3 plus 9 times by 16 to 12.6. Alright, so there it is, and now we can just work out the mole of aluminium nitrate. So that's done by taking 1.39 and dividing it by 212.6. So when we do that, .39 divided by 212.6 is 0.065 0.06538. .06538 mole. Okay, so that's the mole there. Alright, I'm just going to fix this up. If we wanted to do it to correct significant figures, we look at that value. That's 3 significant figures, so we need to do 3 significant figures. That's these values here, cut it off there. That 8 boosts the 3 up to 4. So it's approximately equal to 0.00654 mole. Correct to the 3 significant figures. Alright, so that's that question. Now, find the mole of ions. Okay, so for this you need to understand how ions form. So, and like figuring out from a chemical formula how many ions you have. So aluminium nitrate. Okay, so the way this works is to figure out how many ions you have, for every one aluminium you need 3 nitrates. Okay, you can see that there's 3 nitrates to neutralize the charge. So overall there are four ions. There's an aluminium, and there are 3 lots of the nitrates. So that's 4 ions in total. And so what we can do is, once again, we can work out this. We can look at this kind of table where we're comparing aluminium nitrate to ion amount. And so one of these have 4 of those, 10 of these have 40 of these, and so you can see that we're timesing to go from the molecule to ions, we're timesing it by 4. And so to work this out, you need to figure out, to work out the mole of ion, you need to take the mole of aluminium nitrate and times it by 4. So that means whatever mole we had, which was, we'll use the more accurate answer, 0.006538 times by 4, that's going to give us that's going to give us times by 4, 0.0615 2615. Which again we have to, because this is important to do significant figures, so your answer is going to be approximately equal to, it's 3 sig figs, meaning that it's going to cut off between 1 and the 5, and that means it's 0.0262 mole of ions. Okay, so the next question is calculating the number of them, the number of ions. Okay, so the number of ions, well, we already know the mole of the ions, which is equal to, I'm going to use a more accurate answer because when you times it by Avogadro's constant, it's going to get, because Avogadro's constant is such a large value, it's going to affect the accuracy. So the number of the ions is that times by Avogadro's constant. Avogadro's constant, which is equal to, and we've got that on our screen there, 6.022, 0.7 and 0.1, 1575, because times 10 to the 23, which is equal to, we're just going to 7 times 10 to the 23 ions. So what I've done is I've just got it to the correct significant figures, which is 3 in this case, and I've expressed it that way. So that's what the value is. Alright, the next question, find the number of atoms. So whenever we're finding the number, we are looking at capital N. So number of atoms. Well, we need to once again have a look at the relationship between molecules and atoms. So we know that this is our original formula, NO3, 3, and one of these we can figure out how many atoms there are. There's one aluminium, there are 3 nitrogens, so 1 plus 3 plus 9 of the oxygens. So if you add this up together you get 13. So the relationship between aluminium to atoms is times by 13. So yeah, we need to get a number of, if we can find, where was it? If we can find the number of our aluminium nitrates, and times it by 13, we'll get a number of atoms. So I think we did calculate it somewhere at the top there. Did we? No, we just went straight to, okay. So we don't have that amount, which is okay. We can still find it because we do have the mole. What was it? 6,538. And that was the mole, and then we have to times it all by Avogadro's constant. So that was the mole of aluminium nitrate, and then we have to times it by Avogadro's constant and the 13. And so it's going to give us a 0.006538 times by 13, and then times by 6.022, we get which amounts to 5.12 times by 10 to the 23 atoms. Okay, so we've just calculated how many atoms there are. Alright, question 3 is a very similar question, except this time that you're given a little bit of a different piece of information to calculate. So you're told, it's quite an interesting question because you're told how much mole of oxygen atoms you have in this potassium dichromate. So remembering our little table that we always use to compare potassium chromate, in every one of these there are, if you wanted to compare it to the oxygen atoms, there are 7 oxygen atoms. So this time we're actually going from the oxygen atoms, because we know how much mole of it we have. We're going from the oxygen atom to the potassium dichromate. So we actually have to divide by 7 because we're going the other way. Now, so what that means is to find the mole of potassium dichromate, we need to take how much oxygen we have, which is this amount of mole, and we need to divide by 7. Okay, because that gives us the mole of the entire molecule. Now let me just calculate this again. You can tell that from the table as well. It doesn't matter if you have number of molecules or mole, the factor is still the same. Okay, divided by 7. 0.4285. Okay, so the mole is going to be smaller, and that makes sense because it's not wide 0.49285. Okay, I forgot my 9. Alright, so we've got this here. Now we want to find, and that's our answer, right? So 3 significant figures means that we express our answer to 0.49285, and that increases the 2 to a 3. So therefore it equals, so this is how much mole of potassium dichromate we have. Alright, so then we jump straight to the number of oxygen atoms. Now the number of oxygen atoms you can find by using, if you have the mole of oxygen, which we already do in the question, you can times it by Avogadro's constant straight away. So we know that we have 3.45 mole of oxygen. We have to times it by Avogadro's constant. 2 times 10 to the 23. Alright, so let's do that now. I'm just going to times this by 7 and then times that by Avogadro's constant, so 6.022, 20.7759. Okay, and that's Avogadro's 59. Okay, I keep missing one number. Okay, so that's 59 times 10 to the 23, and so that's actually going to be 2.07759 times 10 to the power of 24, which, correct to the 3 significant figures, we cut it off there, and that's going to be 2.08 times 10 to the 24. So that's correct to the 3 significant figures that we needed. Okay, next question, the mass of potassium dichromate. So we don't know the mass of potassium dichromate. So we can work this out by taking the mole of the substance and timesing it by the molar mass. So the mole we already found from question A. It was this amount here. I'm going to use a more accurate answer again. 0.49285 times by the molar mass of potassium, potassium dichromate. So let's go back to our periodic table. Potassium's 39.1. Alright, 39.1 times by 2 plus, I think chromium's 52, we'll check in a second. 52 times by 2 plus 7 lots of oxygens. 7 times 5 is 16. And we should be getting a value. Let me just double check that potassium, that chromium is 52. Yep, it's 52. Alright. So 39.1 times by 2 plus 52 times by 2 plus 7 times by 16, 294.2. And we're timesing that by 0.49285. And when we do that, we end up with 0.49285. 144.99. Okay, again, 3 significant figures means that that answer is just going to be 145. Okay, so that's our mass of potassium dichromate. Our number of ions, number of atoms is calculated in a very similar way. You can again set up your little table where you are going to be looking at potassium dichromate and ions. Now with potassium dichromate, there are 2 potassiums for every 1 dichromate. So dichromate, this whole thing is together. So there's actually 2 plus 1. So in every one of these, the ions is 2 potassiums and 1 dichromate, so 3 ions. So to go from there to ions is times by 3. Okay, so if you have the number of your potassium dichromate, number of them, I think we did calculate it somewhere, didn't we? No, we just went for oxygen. Okay, so we need to, we can use our mole, 0.049285, and times it by Avogadro's constant to first get the number of these, and then to get the number of ions, you can just take this value here times by number, oh well, Avogadro's constant times by 3. And that we can then calculate 0.049285 times by Avogadro's constant times by 3.8903. Times 10 to the 23, and then that simplifies down to 0.90 times 10 to the 23. So that's how many ions we have. Oh, sorry, I didn't reduce that power, did I? That needs to be 22. Okay. Excellent. So, number of atoms. Okay, so with this one, number of atoms is going to again depend on our table. We draw this to avoid confusion. So potassium dichromate, for every one of these there are the number of atoms. You have 2 potassiums plus 2 chromiums plus 7 oxygen atoms, so that gives you 11. So to go from this to this, you have to times by 11. Okay, so once again we're going to be using our lovely Avogadro's constant, and the number of atoms is going to be calculated by taking again that value, the potassium dichromate value, timesing it by Avogadro's constant, and then timesing it by a further 11, because we know we need to. Okay, so that gives us a value. Okay, I'm going to clear this. 0.049285 times by 11 times by 6.022. So 3.26 3.26 times 10 to the 23, and that's directly our number of atoms there. Okay, Question 4. Question 4 says, if there are that amount of molecules of oxygen. Now, this question's being quite technical. Molecules of oxygen is not the same as oxygen atoms. Molecules of oxygen means O2. And that's how many there are. So the number of O2 happens to be 5.5 times 10 to the 22. And you want to find the number of oxygen atoms. So once again, we can draw up a table. In every one of these, there are 2 oxygen atoms, aren't there? If you have 10 of these, you would have 20 oxygen. So the relationship between this and this is times by 2. This is atoms. And that's molecules, right? So if you want to find the number of atoms, for A, we need to just find out, well, we've got the number of oxygen molecules given to us, but we want to find the number of oxygen atoms. So we go 5.5 times 10 to the 22 times by 2 to get atoms of oxygen. So that's going to be 11 times 10 to the 22, which is 1.1 times 10 to the 23. Okay? So that's how many oxygen atoms you have. Now the mass of oxygen molecules. So the mass of oxygen molecules is unknown. Now we have the number of them. If we want to go from number to mole, we can do that. The thing is, if you remember from this flowchart, mole to get to number, capital N of anything, you have to times by Avogadro's constant. If you're going the other way, you're going to be dividing by Avogadro's constant. So this time we have the number of oxygen molecules. We need to divide by Avogadro's number to get the mole. Okay, so to get the mole of oxygen, you need to take 5.5 times 10 to the 22 and divide it all by Avogadro's constant. Now, making sure that you have brackets around these when you're inserting it into a calculator, otherwise it will give you a very weird answer. It might even have like 10 to the 47 or something ridiculous like that. You don't want to be incorrectly placing it into your calculator, right? So 5.5 times 10 to the power of 22 divided by Avogadro's constant, which is 6.022 times 10 to the 23. Okay, 0.09133. So that's how much mole we have of oxygen. And yeah, we're going to be placing, we need to find the correct number of significant figures, which in this case happens to be 2 significant figures, as you can see from there. Those are the numbers that you take into account. These are just place values, so you don't look at that. So 2 sig figs means right there we cut off, and the 3 doesn't increase. So it's just this. So that's how much mole of oxygen you have. And the next thing to find the mass is you have to take the mole of oxygen and you need to times it by the molar mass of oxygen. So we already know that it's 0.09133, and the molar mass of 2 oxygens is 2 times 16, which you can then figure out, and that should give you your mass. So times by 32, 2.922. grams. That's correct to the number of significant figures. Or actually it's not, it's 2.9 would be 2.9 grams. Okay, so question 5. Question 5, okay. So we're doing well here. Now, we are told here how many hydrogen atoms there are present in phosphoric acid. So once again, straight away, I already know that we're looking at hydrogen atoms. We have phosphoric acid, H3PO4. In every one of these, we have 3 lots of hydrogens. So to go from, what do we want to do here? Okay, we have the hydrogen number. So we know what, it's 8.83 times 10 to the 24 of these. If we wanted to find the amount of phosphoric acid molecules, we actually need to divide it by 3. So we need to take this value and divide it by 3. So that's the number of phosphoric acid molecules. 8.83 times 10 to the 24 divided all by 3. And that should give us a value. So 8.83 times 10 to the power of 24 divided by 3. Great. What I'm going to do instead of that is I'm going to go 8.83 divided by 3 because my calculator is not cooperating. So it's 2.9433. times 10 to the 24, and that's 3 significant figures, so 3 significant figures cuts off there, and that's still, that doesn't change the 4. So this is how many particles and molecules we have. Okay, the next question B continues on from the question above. It asks you to find the mass of phosphoric acid. So first of all, we need to go and find the mole of phosphoric acid. So in order to do that, we need to take the number of them that we have, and we need to divide it by Avogadro's constant. So that will give us the mole. Making sure you have brackets, okay? So (10 to the power of 24 divided by 6.022 times 10 to the 23. 4.8876. mole. Okay, so next, after we've figured out the mole, we have to find out the mass. And the mass in this case is 4.8876 times by 3 lots of hydrogens. This is just working out the molar mass, okay? Plus phosphorus. I've forgotten phosphorus. I think it's 39, but I can't be sure. No, it's 30. It's 31. 39 was potassium. Okay. 31 is phosphorus. (31) plus 4 lots of oxygen, which is 16. Okay, so that allows us to calculate this now. So 3 plus 31 plus 4 lots of 16, 98 times by 4.8876. Okay, so it's quite a large number, but that was quite a large mole, so it's 478.98. Which, correct to the number of significant figures, it's 3, so we cut off here, and that 9 increases this one, so it's approximately equal to 79 grams. Okay. So the next question, find the mole of oxygen atoms. Okay, so we know already that the mole of H3PO4 was equal to 4.8876. Now what we need to do is to figure out the mole of oxygen atoms. We need to times it by 4. Again, we can do the table, but after a while you get used to recognizing how many oxygen atoms there are, and you can stop doing the table unless you're still getting confused. Okay, so 4 times by 4.8876 will give us the mole of oxygen atoms. Four times by 4.8876, 19.55. Which again, to significant figures, that's going to cut off there, the 5 is going to increase the 5, so that's 19.6 mole. Okay. Find the mass of oxygen atoms. Okay, so this is going around in circles. It's to find the mass of oxygen atoms, you have to use the mole of oxygen atoms and times it by the molar mass of oxygen. So we just figured out the mole of oxygen. Use a more accurate answer, times it by the molar mass of oxygen, which is 16. And then you can figure out so 312.806. Which is approximately equal to 313 grams. Alright. So that's that one. And finally, we've got find the mass of phosphate in the sample. So we're looking at one of them, phosphate. Mass of phosphate. Well, phosphate is PO4 3-, and we're trying to find the mass of this. So once again, if we look at our molecule, in every one of these, there's actually only one phosphate In every one of these there's one of these. And so if we begin with the mole of phosphate, the mole of phosphate is going to be equivalent to the mole of H3PO4. Because I showed you just there that to get from there to there you just have to times it by 1. So that affects the mole. We know the mole of this part, right? We already calculated it from above. So we know that the mole of phosphate is equal to 4.8876 mole. And then after that we can find the mass. So that's the question. So we take the mole, how much we have, and we times it by the molar mass. Now the molar mass is 31 plus 4 lots of 16. The charge doesn't make a difference. It's a charge. It's a bunch of electrons. Okay? So they're negligible in weight. 4 times by 16. 95 times by 4.8876. 464.33. So that's most of the molecule. 463. And it's the majority of the molecule because I mean, hydrogen doesn't weigh much. There's 3 hydrogens, and these are not going to compose much of the mass of the molecule because hydrogens are just 1 mole of hydrogen weighs exactly 1 gram. So it's not, so if you have 6.022 times 10 to the 23 atoms of hydrogen, it's only going to weigh 1 gram, so it's very light. So phosphate is going to make the majority of the weight. And you can cut this again to the number of significant figures that you're meant to. That's how many grams it is. Okay, so we've completed 5 questions. We'll have another video that completes the other 5 questions that are in this worksheet. But for now, try to practice a little bit more and then watch the next video to just get some extra boost in confidence. Thanks.